I'm Dr. Karl, coming to you from the lands of the Gadigal people of the Eora Nation. I acknowledge Aboriginal and Torres Strait Islander peoples as the first Australians and traditional custodians of the lands where we live, learn and work.
G'day, Dr. Karl, Shirtloads of Science, University of Sydney with Dr. Matt Agnew, famous for many things, including writing the book, Is My iPhone Reading My Mind? But you've been trained as
I've got a few hats. Engineer, undergraduate.
What sort of engineer?
Mechanical. So I did a double degree engineering mechanical and Bachelor of Science, majoring in applied mathematics, minoring in computer science. Bit of a mixed bag.
That's good.
But all very analytical.
Yeah.
Worked as an engineer for several years. I was over in Western Australia, like every second person there that did engineering. I did FIFO, I was working in oil and gas fields.
We haven't got to your book, Is Your iPhone Reading My Mind? So you worked as a FIFO. That's terrible on your life and your health.
It's brutal. It sounds great on paper, working 2 weeks on and then having 2 weeks break, but those 2 weeks on are brutal. Yeah.
And then you got the 5-hour flight over, squashed in the plane, doing so many flights that you end up getting frequent flyer points, and occasionally you can travel in business class.
That's it. Yeah, mostly just squashed. Really tiring work. Certainly financially, it's very lucrative. Yeah, there's health, there's relationships, there's a lot of things you're kind of conceding, I guess, when you do that.
Okay, so we're heading towards you becoming an astrophysicist, having done mechanical engineering, Bachelor of Science, computer science, applied maths. Yep. By the way, what's your favourite equation?
Oh, I mean, this is probably as cliche as it gets, but it's probably Euler's equation.
I love Euler's equation. E to the I pi plus 1 equals 0.
Correct.
Oh, God, isn't that beautiful?
It's the elegance. It's just, it's delightful. So I know it's a cliche answer, but it really is
what
great.
it is. Like some people like Pythagoras, and Pythagoras works, and the quadratic. And a lot of people like Navier-Stokes, and a lot of people like various ones of Einstein's. But you've got three of the fundamental constants that run the universe. You've got E, 2.718, which is related, etc. Related to the exponential growth and logarithms.
Yep.
And then we've got
I. We've got the complex variable.
The
square root of minus 1.
Which sounds stupid because if you multiplied 1 by 1, you get 1. If you multiply minus 1 by minus 1, you still get 1. How do you get two numbers multiplied together to give you minus 1? Well, that's I.
That's where I comes in.
It turns out to be useless, but electrical engineers need it to be able to design a grid to give electricity into your house when three-phase comes in.
Very useful. And I got to do, as part of the engineering, it's a very general engineering the first year when you're figuring out which discipline to major in. And so I got to do some electrical and electronic engineering. So I got to see firsthand the sort of equations that you can solve with imaginary numbers. Gaining that context, I think, is useful because it's very hard, I think, when you explain the idea of imaginary numbers, what is the point of them?
What's the point? So you got E raised to the I by pi. Tell us about pi.
Pi, so the ratio of circumference to the diameter of a circle has been obviously tremendously important for any kind of geometry and trigonometry, but I feel like its applications transcend just that field of mathematics.
Then you've also got the fundamentals of counting, which is 0 and 1.
Yep.
And you've also got the fundamentals of algebra, like plus and equals.
Yeah.
All of that in one little equation.
And so neat. Neat.
God, I love it. I've met a few mathematicians who've had that equation tattooed onto them. Okay, so then you're working FIFO in Western Australia for how many years?
About 3 years.
Okay, and then you went into?
Was a bit disenchanted by engineering, and I thought I needed a bit of a change. And so when I was figuring out what did I like as a child,
before you became famous on TV,
So
as the Bachelor,
So trying to decide. My parents, they said, when you're trying to figure out something, okay, go back to the fundamentals. What did you enjoy as a kid? But I loved space, like many kids, and I thought astrophysics is space for adults. Give it a go. So I did the masters, 2-year masters in Sweden, in Lund. That was 50-50 coursework research.
Yeah. What sort of research did you do?
My master's thesis was on exoplanet atmospheres. And so it was modelling the atmospheres of a class of planet called hot Jupiters. I don't know if you're familiar with this particular flavour of planet.
So it goes like this, audience. We've discovered about 5,000 planets so far. Of those planets, the most popular 2 planets are not in our solar system.
Yeah.
Okay, one of them is a hot Jupiter. So our Jupiter is out in the sticks.
Yep.
It takes 10 years to do an orbit, but a hot Jupiter can do it in
days
or hours.
Yeah.
So it's close in and hot.
Hugely close.
And the other one is the super Earth.
or
5 times the size of the mass of Earth. We don't have one of those.
No.
What's going on? We don't know. So you're modelling hot Jupiters.
Yes, and the reason we do that, or the reason that's kind of the first target for modelling atmospheres, is because they're so close. the heat puffs up the atmosphere, and so they've been really typically quite easy to observe the atmospheres of these planets. And when I say observe, we're not looking at them, but the light of the star can shine through the atmosphere, and we can understand the chemical composition of the atmosphere based on how the light interacts with the atmosphere itself.
Yeah, so you can stare at the star and you're getting a certain quality of light coming from the star.
Correct.
And our hot Jupiter's on the other side, so hot Jupiter doesn't come into it. Then hot Jupiter comes around the corner, and then suddenly the light from the star shines onto the hot Jupiter, so there's an extra bit of light. And then it comes around in front of the star, and for a brief moment, the sunlight is shining through the atmosphere of the hot Jupiter.
Correct. So,
okay, is that what you were looking at, that brief moment?
That informed the modelling. This was a theoretical or computational research project, but the data we used to base or build that model was around this real data that was being observed around hot Jupiter atmospheres.
Wow, we haven't even got to the basics yet. So what did you discover?
Thermal inversions. So thermal inversions being as you go up in altitude, the temperature decreases
on planet Earth.
In our atmosphere,
until you get to a certain level.
Till you get to a certain height, and
why does that happen?
Basically, the interaction of light with the chemicals in the air, how the energy from the light is being kind of going through the layers, and you get different effects at different temperatures, and things like greenhouse gases trap light and trap heat underneath the greenhouse gas kind of layer. But you've got other interactions. So where you have like water crystals, when you have ice crystals, there's kind of different interactions in that area. The specific molecules I was looking at was iron oxide, Fe2O3. I think that was, there's a few of them. That's chemistry.
Yeah. Chemistry is just the physics of the outer electrons.
That's it, yeah.
It's not a real science.
Yeah.
We're being mean to the chemists. We apologise, sorry. Getting back to Earth, so the radiation from the sun goes through the atmosphere at a temperature of 5,500 degrees roughly.
Yes.
Doesn't see the greenhouse gases, goes straight through, heats up the ground. The ground then heats up to 15 degrees C. It radiates heat at 15 degrees C up, and at that temperature it does see the greenhouse gases, and some of the heat gets bounced back down to the Earth, and so the greenhouse gases are trapping 600,000 Hiroshima bombs worth of heat each day. That's a big number, isn't it?
That's a big number,
okay,
yeah.
So you were looking at hot Jupiters?
Yes,
and?
yes. And so essentially I could create a particular set of initial conditions, because a lot of it was kind of, these are dynamic systems, so we're obviously very sensitive to initial conditions. And so I was playing around with different conditions, different ratios of chemical compositions, few different variables to try and understand what circumstances would lead to a thermal inversion and what wouldn't, and is it likely to be taking place? And the results were, yes, it can. I had sort of this matrix that I had built out that we were varying two variables in particular, and we're identifying this is, under these conditions, this is where you expect thermal inversions. But I also had some kind of secondary and tertiary outcomes that came out of it as well, such as we had this sort of stable cyclical situation where you'd get particular crystal particles in an area that would then heat up, but then the heat would drop the crystals down to a lower state of matter, which then would remove that sort of heat trapping, that would then create clouds that would then rain out and precipitate out the iron, which would then allow it to then heat up. And so we had this sort of weird cycling through these different states, but in a sort of stable loop. It was kind of not the prime outcome, but it had this sort of, this would happen, which would cause this, which would cause this, which would cause this, and then it would back to the start again. And so there was this sort of stable cycle of, it was sort of cloud, rain, no cloud, crystals, back to cloud again.
Wow, so this is in your master's in astrophysics, so I'm guessing you did a PhD?
Did a PhD.
And where was that at?
So that was at Swinburne.
Okay, in Victoria. And what was your topic there?
So that one was a dynamical search for habitable worlds and solar system analogues. So stayed within the world of exoplanets.
Yeah.
Again, stayed within the world of theoretical and computational astrophysics. But this time I was, rather than simulating or modelling atmospheres, I was simulating and modelling planetary systems. Maybe I've got this thing for Jupiter. It was systems that had a Jupiter-like planet already observed, and ideally a Jupiter-like planet that was orbiting outside of where the habitable zone was. So it's
outside the habitable zone.
So similar to what we've got going on here in our solar system.
So habitable zone is where water can be a liquid, not frozen into ice and not hot enough into steam.
In particular on the surface, liquid water on the surface,
Okay,
which requires also an atmosphere as well.
Now, how did you end up becoming the fabulously handsome bachelor on TV? Tell us about that part of your life. You have to tell us about that part.
Yeah, so that was, I guess at the time I was working in research. I was completing my PhD.
Oh, you were doing your PhD at this time?
Still doing my PhD. I was single. I was dating.
Yeah.
Was on the dating apps like everyone was then, and certainly kind of everyone is still.
Yep.
Wasn't having a ton of luck, and I thought, this was a dating show. I'll throw my hat in, and I'd actually applied for the sister show to The Bachelor, The Bachelorette, and in that circumstance, you've got a bachelorette. And you've got female person, and you've got a bunch of male peoples
who then vie to be the one.
You're one of the many. And
Little did you know that you were good enough to be the one of the one.
They had lined me up for the one of the one. Yeah.
Really?
So that's how.
So you were that handsome, clever, athletic, all those things.
Look, I think maybe it was more of a novelty. I don't think they had very scientific or astrophysical careers to date. So it was I think it was more the different spin. It was a fresh coat of paint on the show compared to some of the other people that had athletes, doctors, chiropractors, all kind of various career paths.
Can you tell us what happened, and did it last forever and you have 15 children, or did you end up shooting each other in half an hour after the show finished, or what?
Somewhere between those two extremes, I'd say. We dated for some time.
So you chose one person?
Chose someone.
So how do you choose, knowing that they're all putting on their best face, which might not be their real face? It's
hard. You're kind of trying to assess them. I mean, you go in assuming people aren't that good of an actor. Kind of to hold up a facade for that extended period of time is quite hard. So you go in with the best intentions, and you assume you're getting the genuine, authentic people themselves that you're talking to.
So from your point of view, they're saying, look, we're going to give you some money, which is very handy if you're a PhD student, and we'll get you a girlfriend, and we'll put somebody who's psychologically appropriate for you, a bunch of them, and I mean, it sounds like a really good deal.
Yeah.
It's a good start for that. Yeah.
And also, again, being a scientist, I'm sure you can appreciate this. The success rate up to that point was about 50%, which
what do you mean by the success rate?
In terms of from the shows, the person who's gone on it, there's roughly a 50% success rate in terms of them ending up in a successful marriage, kids, whatever. And so there was kind of some good numbers backing up the whole process. I think there had been 7 seasons of The Bachelor. There'd been, I think, 5 of The Bachelorette, and 50% roughly had ended up in long-lasting, loving relationships, sometimes marriages, sometimes kids, sometimes both.
Oh.
So, going into it, I thought, okay, there's actually, being a numbers man, there's actually a good kind of success rate here.
And they've gone to the trouble of finding people who are nice and compatible with me.
Yeah.
Wow. What's not to like?
That's it.
It's a great offer. So you took it.
Yeah, I did take it. Yeah. Unfortunately, it didn't work out for me. I did pick someone who there was obviously a lot of compatibility. But like any relationship, sometimes it just doesn't work out, and that was unfortunately the case for me.
And then since then, you've been writing books.
Yes.
Including this book.
Yes.
I think we're going to have to go to a part 2, but before we go to part 2, tell us more about your previous books.
So the first book I did came out at the end of 2022, and that was Dr. Matt's Guide to Life in Space.
Lovely book.
Loosely around my PhD, I'd say. I'd kind of dabbled in, like I said, exoplanet atmospheres, habitable worlds and searching for them. And so it was, I leaned a little more into the world of astrobiology and habitability of, planets, but also moons in our own solar system. And then a little more, you've read it, the bit more creative license towards the end there, but still kind of trying to keep a foot firmly in the world of science. Writing a book is quite liberating compared to the rigidity of scientific journal writing.
4 test tubes were obtained, and then the computers were switched on instead of I switched on the computers. It's all passive voice.
And even like I talk about the Nice model and the Grand TAC model of solar system formation. There's a few competing hypotheses, but that's the one, in my view, the strongest case and the most evidence. But there are other hypotheses, and I got in a bit of hot water with my first paper I submitted for publication because obviously it's a blind process. You have no idea who the reviewer is, but it came back with a quite firm, assertive, resistant review.
What, resistant to grand tack or niece?
Well, there was a big sticking point in the kind of the lit review portion of the paper where I was discussing solar system formation and the current existing state of the art, and I hadn't done enough to acknowledge these alternative hypotheses for the solar system formation.
Right.
I'd kind of talked about the Nice model and the grand tack model,
and not the other
to
one.
exclusion of all others.
So the grand tack model fits in with that whole thing of why don't we have the most popular things in our solar system, a hot Jupiter or a super Earth. And so it starts off with a Jupiter and a Saturn and a bunch of super Earths close in. And then the Jupiter comes in for various physics reasons, trailing Saturn behind it, which is the big difference. It then comes into the inner solar system, via gravity, it makes all the super Earths run into each other and break themselves up into rubble, and then gets towed out again by Saturn, and then the rubble turns itself into the little bits of rubble that we are today. Is that kind of the grand tack?
That's, yeah.
And what's the Nice model?
Essentially the same sort of thing, that the gas giants formed first, and due to the motion of the gas giants, that's where we kind of are left with what we see today. The Nice is probably a more generalised form of the grand tack model.
And so you mentioned your PhD, so you enjoyed your first book. Look, we're up to the 20-minute mark. We are going to have to do a separate podcast on your book, which we haven't actually done yet because you're such an interesting person, which is My Phone Reading My Mind?
Came out July 30.
July 30 of the year 2024.
Yep.
And I think we should just admit we didn't quite get to it. We'll do a whole podcast. We won't even talk about you and your fascinating career. So just before we come to the end and then dive into the next one, how can people follow you and your fine work?
The best place to follow me would be Instagram and TikTok. Both of them, my handle is Dr. Matt Agnew, all one word.
DrMattAgnew.
That's the one, yep. I talk about all the latest things that I'm working on. In this specific case, it's the book largely, but I also create regular science content, answering questions and trying to break down curiosities that people have about not just space and AI, but science broadly. And I really love it because when someone hits me with a question that I don't know, I mean, you'd agree.
All the time.
And it's so fabulous,
the
learning experience of, actually, that's an interesting question. What is that smell after it rains? And it's called petrichor. But yeah, I think I love fielding the questions, especially the questions that sometimes get submitted by parents saying, my kid asked me this, because questions kids hit you with they're the best. They're the ones that stump you the hardest, I think.
We'll meet you on the other side in part 2. Finally getting to your book, Is My Phone Reading My Mind? Thank you very much, Dr. Matt.
My pleasure. Thank you.
Shirtloads of Science is washed, spun and aired by the University of Sydney.